engineering simple. In this video, I will show some calculations with respect to core losses and load losses or copper losses. These are important calculations if you are preparing for the FE or PE exam. So let's assume we have a single phase two winding transformer So basically you have the primary, for instance. This is the polarity mark. You have the secondary. Here's the polarity mark. So there's winding 1, and here's winding 2. So let's assume this is a 20 kVA 480 volt on winding 1 to 120 volt on winding 2. It's a 60 hertz frequency. So during testing, short circuit test, this is the information that was measured. So rated current was circulated at rated frequency to the 480 volt side, or winding 1, with winding 2 over the 120 volt side, winding 2 shorted. And this is basically how practically the test is done, on transformers to determine load losses and also impedance, the positive sequence impedance. So basically you have winding 1, winding 2, winding 1. You circulated rated current, if we call that I1, since this is winding 1 and this is winding 2. And winding 2, basically you shorted, it was shorted for this test. So the meters measured the following quantities: V1 is 35 volts, and P1, which is losses basically, is 300 watts. So this is the short circuit test. For the open circuit test, rated voltage applied to winding 2 with winding 1 open. With winding 1 remained open during the open circuit test. So basically you have so if I flip these, here's winding 1, here's winding 2. So you applied voltage, rated voltage, to winding 2, and winding 1 stayed open during this test. So the meters in this test measure the following quantities. I2 is equal to, this is voltage, I2 is equal to 12 amps, and P2 during this test is equal to 200 watts. So these are the two tests that were performed. So now, from short circuit test, from short circuit test, determine the series impedance. Determine the series impedance. The series impedance determine the series impedance, which we can call the equivalent impedance 1 is equal to R equivalent 1 plus J times X equivalent 1, referred to winding 1. Referred to winding 1. Neglecting the shunt admittance. In this case, neglect shunt admittance. Because in general, the model for the transformer, so you have the windings here, and obviously you have the secondary resistance, and you have some reactance associated. Then you have a shunt kind of admittance here. Then you have a resistance, a reactance to the primary. But since in this case the shunt here admittance, we're ignoring it. That's what this statement is saying. So that's question number 2. Now from the open circuit, test, determine the shunt admittance. Determine the shunt admittance. We can call it Y m is equal to minus, or sorry, GC minus J times 1 is conductance, this is conductance, that's susceptance. Referred to winding 1. Neglect the series impedance. The series impedance. So how do we tackle this problem? And basically, like I was saying, these are two tests that are performed on transformers in general. One is a short circuit test to determine the positive sequence impedance, and also what's called load losses, or sometimes copper losses. The second test, which is the open circuit test, which is to determine the excitation current. Basically, it's the current that needs to flow in the core in order for the rated flux to flow in the core. And also you determine the core losses, or no load losses. So part A, so basically we're applying voltage to winding 1. So we'll have R equivalent 1, and we have a reactance, J times equivalent 1, and we're ignoring the shunt admittance. So we have, here's the winding 1, here's winding 2, and basically we are shorting the secondary or winding 2. So we're applying V1 to circulate the rated current, so I1 will flow. So it's important to write or to make the sketch to understand what's going on. So this side is 480, this side is 120 volts, so that's kind of the ratio. So the rated current is equal to S1 rated divided by V1 rated. So it's 20 kVA divided by 480 volts because it's on this side. So this is 41.667 amps. So that's the rated. So let's keep that in mind. So the resistance, the equivalent resistance referred to the winding one side is equal to P1, which was measured during the short circuit test, divided by I square 1 rated, because we circulated a rated current, which is equal to 300 watts divided by 41.667 squared, which comes to 0.1728 ohms. If you want that in percent, so that's in ohms. If you want it in percent, you take P1 divided by S1 rated, which is 300 watts divided by 20 kVA, which would be 0.015 per unit, or 1.5%. So we know the magnitude of the impedance referred to the winding one side is equal to the voltage measured during the short circuit test divided by the rated current, which is what was circulated. So it's 35 volts divided by 41.667 amps, which is equal to 0.84 ohms. And we know impedance is equal to, these are magnitudes, the square root of R equivalent 1 squared plus X equivalent 1 squared. That means X equivalent is equal to square root of Z equivalent 1 squared minus R equivalent 1 squared. So if you plug all the numbers, you get this is equal to 0.822 ohms. So that's a reactance. And we know impedance is equal to resistance plus reactance, so 0.1728 plus J times 0.822. All this is in ohms, and you can put in polar form 0.84 with an angle of 78.13 degrees ohms. So how did I find this 0.84? It's just right here. If you want the impedance in per unit, so the Z equivalent 1 is equal to V1 that was measured divided by V1 rated of the winding that was applied. We applied the test to it. We measured 35 volts divided by 480 volts. So this is equal to 7.29%. So that's kind of how you do the calculation. So that's for short circuit. That's now for the open circuit. We have conductance and we have susceptance, or minus J times B. So we applied rated voltage so for this is the winding 2, which we applied the rated voltage. So V2 is equal to 120 because we applied it to the winding 2, and the circulated current is I2. Then obviously you will have voltage here, and the ratio on this side is 480 volt, this side is 120 volt. So when now V1, because this current here, since this is not connected to anything, so the current is 0, so V1 is equal to E1, which is E1 is kind of like across the winding, which is N1 divided by N2. So N1 on this side, number of turns on the winding 1, number of turns on winding 2, times V2 rated, which is 480 divided by 120 times 120, which is that just 480 volts, which is expected because winding 1 is open, is not connected to anything, so there's no current will flow. So V1 is basically the same as the winding voltage, since we neglected the series impedance. So conductance GC is P2, or losses measured during open circuit test, divided by V1 squared, which is 200 watts divided by 480 volts squared, which is 0.0000868 backwards ohms or Siemens. And the magnitude of the shunt admittance is N2 divided by N1 times I2 divided by V1, which is 120 divided by 480 times I2, which is measured 12 amps, divided by V1, which is 480 volts. So if you calculate that, you will get 0.00625 Siemens. So BM is IM squared minus GC squared. So if you plug in the numbers, you will get 0.006195 Siemens. In other words, Ym is equal to GC minus J times VM, which is 0.000868 minus J times 0.00619 Siemens. So that was it for this video. Thank you and have a great day.